Hello and welcome everyone. So I want to start off with this particular problem here. We have something that looks like this here. So my Aunt Carol has a flower bed shown to the left. She's going to cover the bed with square plots. Now I forgot to mention that these were right angles here, so I'm going to go ahead and do that. And we want to cover the bed with square plots, 1 foot on the side. How many will she need? And of course for this problem here, assume that you can of course cut the plots, excuse me, to fit within the boundary of the bed. Okay. So again, pause the video, give it a go for you, and see what we can come up with. Now, there are quite a few solutions for this problem here. There are quite a lot of things that you can do with this, right? So probably the standard method here is to sort of drop a vertex like this straight down, drop a line from this perpendicular to the base here. I've got a rectangle here, so this is 7 by 6, so there's 7 on the bottom here, this is 6 over here, and then we have this 10. Since this is 7 here, this segment is 7 here, and this entire length is 10, we're going to end up with 3 here, right? So if we, I guess I can use the name here. So we dropped a perpendicular from D down to BC, call it E here. So note that the quadrilateral here, it's pretty clear that ABCD's area here has an area equal to 7 times 6, because in this situation, 7 times 6 is not hard to show this here, right? We know that, plus 1/2, so this is a triangle, it's going to be 1/2 times 6 times 3. So we know that this is going to be, in this situation here, this is going to be 42 plus 9, which is 51 here, right? And we see that ABCD here has 51 of these, we can take 51 of these square plots and plop them into this flower bed here, right? Now, this should remind you a lot of area. And indeed, this is the idea of area here. So what we have here, ladies and gentlemen, is this idea that we can write that the area of ABCD here is like this. Now, one thing to note. This terminology here, you'll note that I put brackets around this. If you see brackets around the name of an object here, name of a polygon, this refers to the area of the polygon. So in this case here, this is going to be the area of ABCD. And notice what we did here is we took this object and we divided it into smaller pieces. In this case, I found the area of ABED here, and then we added the area of DEC, right? So essentially what's going on here is that we've taken this area and subdivided into smaller pieces and put it together in that fashion here, okay? Now this strategy is a very useful one. You're going to be seeing this a lot here, and we're going to keep going with that, okay? So note that we have this sort of thing here, and we can go for it that way. Now wait, Mr. Chung, you may ask, isn't this just the trapezoid, so you can just use the formula for the trapezoid? And you're right, we can. Now, if you don't know the formula of the trapezoid, well, that doesn't help you very much, but at least we can try to figure that out here. So, today what we're going to do is we're going to look at this concept of area. Look at area here. Okay. So here I have here area. Now, the area of quadrilaterals is pretty straightforward here. Most of the quadrilaterals that we're going to be looking at here will be pretty good. For instance, the rectangle is probably one of the first things that you learn about for the area here. So for the rectangle here, the area is just going to be the length times the width, right? And I think that's one of the first things you learn here. Now, why? Well, I mean, it shouldn't be too hard to do this here. If we consider the area as just simply how many little 1 by 1, unit plots, unit squares we can stick into an object here. Well, in this case, if we have a rectangle, we can kind of think of it as a grid, right? So we can have L of these over here, 3, 4, 5, 6, some number of these squares here we can stack like this. So there's going to be, rows of L squares here, right? And notice that, we can create a bunch of these rows by stacking these rows on top of each other. So we can kind of do this here and end up with a grid like so, right? Or, I guess you can end up with a giant chocolate bar, so to speak. So there's going to be W rows of L squares, so it's going to be W times L here, right? And I think the rectangle, you can see here, very straightforward. You should already know this here. And note that similarly speaking here, because the square is just an area, is just a rectangle, right? Where the length and the width are the same, we can just apply this formula L times W here. So we have the side is like this, so the square, the area is just going to be side squared, right? That's pretty straightforward because it's just side times side. That makes sense. Now, we also have our other objects here. We also have, for instance, the parallelogram, right? So the parallelogram's area here, right? The most important part, I think many of you know with the parallelogram here. The parallelogram has an area that's equal to, if you're not mistaken, it's b times h, base times height, right? In this case, here's our base, and the height, as you can see here, is a perpendicular distance like so, right? The perpendicular distance between the bases like this. Now, I'm sure many of you seen this here, and you know what? You might as well continue doing this here. We can sort of, do a little bit of surgery here. We can show that this parallelogram works by simply taking this triangle and kind of lopping it off here. We can take this triangle here and lop it off, right? This entire thing, we can kind of move it so it's over here, right? And we see that we can do this here, and this just collapses back to that of the rectangle. So something like this here is not too hard to show as well. Okay. Now, note that that gets us through quite a bit of the special quadrilaterals here, but there are other quadrilaterals to focus on. In particular, now we can focus on the trapezoid here. So I'm sure some of you already know the trapezoid here. Right? Some of you know that the trapezoid involves sort of like the sum of the bases and the height and all this other stuff here. So there are a lot of ways you can do this here, right? So for something like this, let's say we're going to have our height. So here's our height here. Let's call this h. And then we have our two bases here. I'll call this b1 and b2 here. So there are a couple ways you can tackle this problem like so. One way you can do this, and I think you can see something like this here, is you can just sort of copy the trapezoid, right? Like this. You can take a copy of the trapezoid and glue it over here. So I can take this and kind of do this sort of thing up here where I can sort of create a copy like so. So if I call this A, B, C, D here, right? I can basically sort of rotate around this central point here and move it like this so I can get, the same idea here. So this will be D, but I don't want it to be the same name as that, so I'll call it D hat. Here will be B hat here, right? And we can see that we can kind of do this sort of setup here where this is B1, this is B2 here. So I've got myself a parallelogram yet again. So we know that the area of this case A, D hat, B hat, D, wow, is going to be the base times the height. Well, the height is still the same because this height is all the way through here, but the base is now the sum of these two bases. So it's just B1 plus B2 times H. But since this is double the area of what we want, we know that ABCD here is just going to be 1/2 of A D hat B hat D. So it's 1/2 times the height times base 1 plus base 2. Okay? And I think you can see here, this is our standard formula for the area of a trapezoid. You're going to be noticing this a lot. You can kind of set this up here as well. Alternately, you didn't have to sort of clone this here. You could have subdivided it by drawing in another height from B like this and sort of look at two triangles. Another thing you could have done here is you could have drawn AC, this diagonal here, and note you have two triangles, ABC and ADC. They still have the same idea here. You send up that, okay? So the trapezoid works out very nicely here. Now, there is one other thing I want to focus on here, ladies and gentlemen. That is our rhombus. Note that the area of the rhombus here is pretty straightforward, right? The area of the rhombus is since the rhombus is a parallelogram, you can use area equals base times height. However, I want to use some of the special properties of the rhombus here as well. So consider this. We want to determine the value of ABCD, the area. Now, the nice part about this is that one of the nice parts about the rhombus is that the diagonals are perpendicular, right? So if I draw the diagonals like this, granted, I did not draw this very well, so you're going to have to bear with me. This point here, E, these are perpendicular here, so that means all these are right angles here. Now, okay, the nice part, also another thing to note here is that we have this. So AE and EC are congruent here, DE and EB are congruent here. So I think we mentioned this before. It shouldn't be too hard to show that the rhombus is divided into 4 triangles, and they're all congruent to one another. So therefore, I can write that this is just 4 times the area of one of these triangles, AEB here, right? There's just 4 times AEB. And the fact that this is a right triangle is really, really helpful here, because since this is a right triangle, we can just simply put this together. The base and the height are very straightforward here. So that means it's going to be 4 times 1/2 times AE times EB, right? So in this case, the area of triangle AEB here is 4 times 1/2 times these two pieces here. That's great. Now, let me go ahead and mess around with this a little bit, because I think we can kind of do a couple things. If you know AE here, we know AE and EC are the same. So if we look at the entire thing here, it shouldn't be too much of a stretch for us to note here that AE is 1/2 of AC, correct? Because in this case here, this has been divided exactly in half. By the same token, we can do the same thing with EB. We know EB is going to be 1/2 of DB here, right? Same idea here. Okay, so we can start putting everything together here. Now I can go ahead and substitute this back in and see what happens. So this is 4 times 1/2 times, well, AE is 1/2 of AC, and EB is 1/2 of DB, right? So notice that ABCD, the area of this rhombus here, is now this mess of things here. Well, the nice part about this is that I got a 4, 1/2, and a 1/2. So 1/2 times 1/2 is a quarter. A quarter times 4 is 1. So these actually all vanish. They all cancel each other out. You're left with 1. So what you're left with when all this dust settles is 1/2 times AC times DB. In this situation here, notice what this is. This is diagonals. And this is actually very nice here. So therefore, we can find that the area of a rhombus here is 1/2 times the product of the diagonals here. So it's 1/2 D1, D2 here, where these are the lengths of the diagonals here. Now note here, ladies and gentlemen, this is not too hard to prove. We were able to show this very easily for the rhombus here. And not only does this work for a rhombus, you can actually show that this works for any quadrilateral that is orthodiagonal. That is, the diagonals are perpendicular to each other. If you know that you have a quadrilateral whose diagonals are perpendicular to one another, you can do an argument similar to this here. Granted, it's not going to be as clean because you're not necessarily have 4 congruent triangles, but you should be able to come up with an argument here, an algebraic argument, to show that this is going to be true as long as you have 2 perpendicular diagonals here. Something for you to think about on your own.